we're going to talk about the GLM a tiny bit. There's a lot of applications for lightning with convection. I think Matt and Kim are going to talk about some of those in their presentation after mine on the mesoanalyst, like the strength of using total lightning for the strength of developing updraft and things like that. And there's also some GLM work you can that's been done on the first flash for developing convection with other Go16 products. But today we're going to just talk about the long flash. And there's reasons behind that, and I'll get to those shortly. But as we know, fatalities for lightning have dropped considerably, over the last 20 years. The 10-year average in 2001 was 52 fatalities, and in 2018, that was basically cut in half. And a lot of that has to do with the When Thunder Roars Goes Indoors lightning initiative. And that allowed lightning fatalities to drop to about 48% since the initiative began in 2001. But things like this still end up happening. So this is in 2013 at a Kid Rock concert, I believe. Let me see if I can get my mouse. Okay, there we go. I'm going to do this actually. And then again, this was just last year, maybe a couple years ago. So this was a high school football game, halftime show. With the marching band kids get pummeled by lightning. Lightning strikes near a high school football game, and of course, when James Spann tweets about it, everybody hears about it. But because of that, emergency managers are really concerned about these instances because things like this end up happening. So over 80 concert goers were injured by lightning at the Rock am Ring Festival in Germany in 2016. And you can see these are all relatively recent, even after that 48% reduction in lightning fatalities. And then here's another one, and I believe this was just this past summer, where 6 people were injured from a lightning strike at the PGA Tour Championship in Atlanta. But there's a lot of good things that have happened, and like as I said, when Thunder Roars Goes Indoors, basically stands at this football game. I think this was the University of Illinois or either Illinois State. They clear the stands pretty well a lot of the time. But the big question comes into play is this wait 30 minutes after the storm passes to resume activities. And that is really, really the troubling or the most concerning part about this. And recently, the Weather Service Lightning Safety Toolkit for large venues was updated. And there's a few changes in this that maybe not everyone is aware of. So the events, outdoor, football game, DSS, concert, etc., may resume if all of the following conditions are met. Lightning has moved beyond 8 miles of the venue, okay. The storm mode is taking the lightning activity away from the venue. That makes sense. And then the threat of new lightning strikes within 8 miles of the venue has ended. And again, that is the tricky one, the threat of new lightning strikes, because a lot of times it's easy. It's, maybe convection is just developed and it's moving away from the venue. The lightning is relatively confined. The storms are relatively, for the most part, immature. It's not a real upscale growth into an MCS type situation. Rain has ended. It's a little more cut and dry. So and you notice that there's no 30-minute limit in here as well. So that's another key thing. So as soon as the meteorologist that's supporting the event feels like it's safe based on these conditions, then the event can resume. I think you guys were unmuted, Kim. It's all right. So this may not come across really well on, oh, Actually, it isn't them. It's the recording. So you can see that I have this video of this long flash, and this is what they end up looking like. And I just wanted to kind of give an idea of what that looked like. So that video was shot basically right right here. You can see my pointer just to the south of Jacksonville. And it was pointing to the northeast in this general area. And you can see that there was 2 CGs, but look at the very long flash footprint that was associated um, with that long flash. And that convection was basically from right here, about 50 or so miles to the south of Jacksonville, but that long flash extended all the way up into that area. And you can see by just using in-cloud flashes, Earth Network's total lightning flashes, you can see that there's only a couple, and it's very hard to distinguish. But look at the big, large footprint that GLM ends up giving you for that long flash. And that is one of the real big strengths of the GLM in this situation. So these long flashes have been pretty well documented, at least in research. And this video may not come across real well, but this is one long flash. It was the longest long flash in 2018. I think it was about, yep, right here, 634 kilometers long. It originated in central Louisiana, right in this area, from convection that was moving to the east. But you'll notice it right here, and then it extended to the back. You can see it here on the video, and it just basically propagates westward and northwestward, and then to the north, and then to the south. And it lasted for about 10 seconds or so. But you can see the spatial extent, and many CGs end up falling from these long flashes. There's just enough charge separation in the cloud, from the cloud to the ground, that acts as a path, and you can get a CG, and that's why these are very, very dangerous, because many times it's not raining, and the storms have moved well to the east, etc. Okay, so now we're going to take a look at the conceptual model. So basically, what is physically going on to have these long flashes occur? So this can be best described, in my opinion, from basically the cross section of an MCS. So you can think about this. Here's our convective line. This convective line is moving from, let's just say, from west to east. So westward is to the left on the screen, and then obviously eastward is to the right. You can see that we have front to rear flow from the updraft and then into the anvil, and then behind it, you have this rear to front flow. And a lot of you know this is like the severe MCS conceptual model. So things like rear inflow jet and concepts like that were kind of that were used for this conceptual model, but I'm kind of repurposing it for the long flash, okay? So the microphysical properties within this convective line, within these updrafts, is basically where the lightning activity, that drive most of the lightning activity within the convective line. There's a juxtaposition of supercooled drops, grapple, and ice crystals, basically within this 10 to negative 20 C range, okay? But really, what ends up making the charge separation, because that's what we're really, what's really important here. So when these really small ice crystals, and there's a lot of them in this negative 10 to 20 Celsius range, collide with grapple in the presence of supercooled liquid. These are these little purple circles. What ends up happening is that this ice crystal ends up growing at a faster rate due to diffusion, and because of that, it ends up charging positively. And since those ice crystals within the convective updraft are pretty light, that makes sense, right? Especially when compared to the grapple that's being suspended in the center of the updraft. These very small ice crystals are advected into the top of the updraft, and really they're advected pretty far back into the anvil as well, right? Anvils are really high, and they're made up of primarily ice crystals, but you can see what ends up happening is the anvil ends up being pretty positively charged in this conceptual model. But these are only the smallest ice crystals. Some, not all ice crystals are created equal, and some are larger and heavier than others. And those, they end up being basically thrown back to the west in this conceptual model, away from the convective updraft, they're heavier, so they end up falling and they end up descending. But they're still positively charged after obtaining that charge by colliding with the grapples. But they end up falling maybe 25, 50 kilometers sometimes into the back of this mid-level portion of this MCS, okay? And that's why these long flashes can really extend 25, 50, 75 kilometers, because if you get enough of this positive charge build up here and you have enough negative charge outside of that convective line near the ground, you end up getting these CGs. And there's one other major point here, and I'm going to try, and I'll bring this all together on the next couple slides, is what ends up happening is these ice crystals, because they're heavy and they end up falling, and there's not a lot of upward motion in this area, they end up melting. And what you see on radar is the bright band. And that is pretty important because these long flashes usually, not always, but usually extend to about the extent of the bright band, and basically at the 0C level. Okay, so how do we take that conceptual model and bring it to operations? So I'm gonna basically build an AWIPS procedure for you now. So this is the sandwich product. You can see we basically have deep convection across southeast North Dakota, moving to the east southeast. Very large, expansive cirrus shield. You can see it extends well into Canada. I believe this was a late afternoon this past September. But you can see these are severe thunderstorms. They don't need to be, but in this case they were. So this is like my base layer. And then what I'm gonna do is I'm gonna add my MRMS 0 degree C reflectivity. So I'm looking for the bright band, right? So you can see how, so this is the core of the convection, but you can see how this this reflectivity signal ends up extending pretty far to the north, away from the deep, strong, severe convection, almost all the way basically up into Canada for the most part. So that's the second layer I like to look at, because as I said, these long flashes tend to extend to the length of the bright band. So here's my GLM, so GLM flash extent density, and you can see this is an example of a long flash. Here are my convective cores to the south, but look at this long flash and look how well it extends, and it really maps out into this area. And then, of course, we need basically some kind of ground-based network. And I like to put both the in-cloud and the CGs on here, for this application. But these are all the CGs that fell away from. So it's basically, I think there was like 10 to 12 over this, and this is 1 minute. Over the past minute, based from this long flash, 10 to 12 CGs fell. And you can see one of them actually occurred in southern Canada, probably about 150 kilometers or so, maybe almost 200 away from its parent convection. So you can see how dangerous these could be. Okay, so here's an example, and so I'm going to kind of switch a little gears. These loops don't tend to work real well, so I'm going to basically walk through an example. So you're going to look at, and I'm going to step through these. You're going to look at images every minute, okay, from this event. This one's from August of 2019, and we're going to go through, and I'm going to kind of point out all these long flashes. So this is a severe MCS moving to the southeast. So there's a long flash right there. It's hard to tell exactly if the parent convection was here or here. And they end up occurring every 4 or 5 minutes sometimes. Here's another one, CG's long, far away. Here's another one. So sometimes they occur every minute. There's another good one. But the idea is really they're mapped out super well with that MRMS 0-degree reflectivity. It's really a great application of that MRMS product when you use it with satellite and lightning data for this application. And I'll just kind of scroll through them, but you can see them, and you know they're long flashes because they come and go. So now they're gone. So you look in this area in Iowa, there wasn't, but if I go back to the previous minute, there was a long flash. And then there's another one the next minute, and then there's another one. And really, the amount of long flashes and the frequency of them, okay, really depends on how quickly you can get charge separation back into this part of the anvil or back into this part of the MCS. So if convection is very strong, it's severe, you can imagine a situation where the long flash occurs, charge is neutralized, and then there's so many small positive ice crystals being advected to the back so quickly that it doesn't take really long for charge separation in the horizontal to develop again. And you can kind of see, and I'll kind of keep going through them for this event, but really the MRMS, but look at that one, how nice it kind of maps out. Okay, so here, clearly one of the best ways to use this information is for DSS. So, you have an outdoor event, everyone cleared the stands, and you're moving along, and the storms are well to the east, and you get a phone call, okay, when can we begin this event again? Or when can we begin this football game again? And that's why this is really important, because you can try to provide really good guidance there, right? So one of the things that I like to do is, one, use that MRMS reflectivity, and when that passes, that's a good one. Or sometimes what ends up happening is that signal ends up going away, and just the MCS ends up decaying quick, and all of a sudden the long flashes will stop because there's not enough of that front to rear flow. And because of that, the long flashes just stop, and then you can kind of count, right? So if it was like 15 minutes past the hour, that was the last long flash I called, and it's been 20 minutes since that long flash, in about 10 minutes or so, that's a good idea of that 30-minute time interval. So here's another example from Jacksonville. I'll kind of go through, this is sea breeze convection. So works in North Dakota, works in Jacksonville. Last night there was long flashes in Tennessee. But what ends up happening is, as I'm moving through this, early on, this is all convective core-based lightning. But as this convection ends up dying, what you'll end up seeing is long flashes end up occurring pretty far away from the sea breeze convection that's moving to the southwest. So let's see. So there's all the convective core here, and we'll start to see them shortly. And you can see how that anvil is starting to expand. So there's a couple good ones. There's another one, and this is relatively light rain, if any rain at all, because what we're looking at here is the 0-degree MRMS reflectivity. You can see there's another one there. There's another good one with a CG right near Jacksonville, but that ended up, that long flash occurred from this convection pretty far to the north and northwest. And then there's another really good one. So all this convection is well away from Jacksonville proper here. And then there's another good one as well, extending from this convection. But so you kind of get the idea. So one of the things that we've been doing is we've been promoting this across Southern region. So here I am giving a similar presentation to the Norman Forecast Office staff, and Kevin Klossel, who is seated here. He's one of the emergency managers for the University of Oklahoma. They clearly do a lot of outdoor events. And shortly after this, one of the meteorologists that was there was working in a private in one of their chat rooms, providing DSS to the EM, the local EM at the Oklahoma State football game this past September, and was using GLM and total lightning with a range ring here to provide DSS using this approach. Another way, I think, is to add confidence and value to existing weather service products. Airport weather warnings. That's the example here. This was in February of 2019. I encourage you guys to go and read this. But there was long flashes, and they use this information for airport weather warnings as well. So, the last slide I have, and I think I'm pretty close to time, as as weather service forecasters, we need to add value and strive to provide human-based, IDSS. And really, GLM is the only way you can be confident when assessing the threat of these dangerous CGs from stratiform lightning. And I think they're almost more dangerous because of the situation. Very light rain storms have already passed. And it really allows the forecaster to be proactive when supporting decision makers, core partners, rather than reacting to like an automated lightning system. So this is where the human can really add a ton of value. And that's my last slide. And I believe in weather service forecasters adding value in this way over an automated system, in this situation. So with that, Randy, I will take any questions.